In the previous class, we computed channel capacity for a binary symmetric channel and discussed the significance of it from an engineer's viewpoint. We have seen that the channel capacity is basically limited by the amount of noise which is there on a communication channel. For a relatively noisy channel, the probability of symbol error could be as high as 10 raised to minus 1, which for all practical purposes is not acceptable. What would be expected in a practical scenario would be 10 raised to minus 6 as the probability of error. Now, to achieve this kind of performance, we resort to what is known as channel coding. So, channel coding is basically a mapping of incoming data sequences into channel input sequence and inverse mapping the output channel sequence into an output data sequence. The task of channel coding is performed basically by what is known as channel encoder at the transmitter end and the channel decoder at the receiver end. So, the block schematic of a digital communication system, which includes channel encoder and channel decoder, would be something like this. So, we have a discrete memoryless source. In a practical scenario, this would be followed by a source encoder, but for the sake of simplicity, we have not shown that source encoder, and then the output of the source encoder would really go to the what is known as channel encoder, and then the output of the channel encoder goes to a discrete memoryless channel. This is followed by channel decoder, which is inverse of what happens in channel encoder, and then in a practical scenario this would go to the source decoder, which is again not shown here for the sake of simplicity, and then it goes to the sink or destination. Now, the channel encoder and the channel decoder are both under the designer's control and should be designed to optimize the overall reliability of the communication system. Now, the approach taken is basically to introduce redundancy in the channel encoder in a controlled manner, so as to reconstruct the original source sequence as accurately as possible. So, you could consider that channel encoding is a dual of source encoding. In source encoding, basically we remove the redundancy to improve the efficiency of the encoder, whereas in channel encoder we introduce redundancy to improve the reliability of communication. So, let us see what a channel encoder does, and to simplify our discussion, let us assume that the input to the channel encoder is consisting of binary sequence, that is bits, and what a channel encoder does is that the input message sequence, that is binary sequence which arrives, is divided into a block of k bits. Right? So, again for the sake of simplicity, we will assume the block type of channel coding. So, it takes k bits and then basically it maps to n bits, where n is greater than or equal to k. And then, so we have n minus k bits as redundant. And we also define one parameter, what is known as code rate. R is equal to, by definition, k by n. So, for a prescribed k, the code rate R and therefore the system's coding efficiency will approach 0 as the block length approaches infinity. That means the number of redundant bits, if you keep on adding more and more, the reliability of communication will increase, but simultaneously the code rate will fall down. Now, the accurate reconstruction of the original source sequence at the destination requires that the average probability of symbol error be as low as possible. In a practical scenario, I would like to make it arbitrarily small. So, now the question is that given this scenario, does there exist a sophisticated coding scheme such that the probability that a message symbol will be in error is less than some epsilon? Correct? This epsilon obviously is a positive number, and this could be as small as we desire. Given this, is it possible for me to design a coding scheme which is efficient and the code rate, that is R, need not be too small? So, I want to satisfy these two conditions. So, I am looking for a coding scheme which is efficient and simultaneously the code rate is not very small. Now, is it possible? Fortunately, the answer to this is yes, and we will see basically how is it possible. Okay. So far in our discussion, when we talked about the discrete memoryless source or discrete memoryless channel, time never came into the discussion. As far as the entropy of a source is concerned, we always talked in terms of bits per symbol, and for discrete memoryless channel we talked in terms of bits per channel use. But transmission of information is obviously concerned with time also. So, let us bring in time, and we will bring in time as follows. Let us assume that I have a discrete memoryless source, and this discrete memoryless source emits symbols from the source alphabet every Ts seconds. So, with this source we will have an entropy associated with it, correct. So, this is the average information which I get per symbol, and every symbol is being emitted every Ts second. Therefore, I can say that average information rate is entropy divided by Ts, and this will give me now bits per second. Similarly, we have this information being transmitted on a discrete memoryless channel, and this has a capacity C which is given in terms of bits per channel use. Now, let us assume that this channel is capable of being used once every TC seconds. Okay? So, if this is the condition, then I can define my channel capacity in terms of unit time as follows. So, channel capacity per unit time would be given by C by TCS bits per second. Now, given this, we try to answer the question which I had posed earlier, that is there a coding scheme which is efficient and where the code rate is not very small. When I say efficient means I decide the probability of error epsilon and it could be as small as possible, and then I also want that the code rate should not be too small, correct? Is it possible for me to find out that? And the answer to that is given by Shannon's second theorem, which is also known as channel coding theorem. And this channel coding theorem is given in two parts. Okay. So, what does the theorem say? Let a discrete memoryless source with a source alphabet S have an entropy Hs and produce symbols once every Ts seconds. Right? Let a discrete memoryless channel have a capacity C and be used once every Tc seconds. Then the first part of the theorem says, then if this condition is satisfied, what it says that if the information rate which is given by the left hand side of this inequality is lower than the capacity of the channel which is specified in terms of bits per second, then there exists a coding scheme for which the source output can be transmitted over the channel and be reconstructed with an arbitrarily small probability of error. Correct. So, and C by Tc is known as a critical rate. So, if your information rate transmission is exactly equal to C by Tc, then what you say that you are signaling at the critical rate. So, this is the first part of the theorem, and the second part of the theorem says that conversely, if this condition happens, that means the information rate is higher than the channel capacity, correct? Then it is not possible to transmit information over the channel and reconstruct it with an arbitrary small probability of error, correct? So, these are the things, but it is important to notice that both these conditions, condition number 1 and condition number 2, they do not tell us how to construct a good code. It is only an existence proof. It only says there exists a coding scheme, but how to construct a good code satisfying our constraint is not known. Okay? And the second is that theorem does not have a precise result for the probability of symbol error after decoding the channel output. It only tells that probability of error tends to a 0 as the code length increases, again provided the condition 1 is satisfied. Okay? So, it is important to note this. We will not go into the proof of this second theorem by Shannon, correct? But let us try to give an application of this channel coding theorem to a binary symmetric channel, correct? Okay. So, we will consider the application of channel coding to a binary symmetric channel. Though we are not going to the formal proof of this Shannon's second theorem, that is channel coding theorem, earlier when we were trying to discuss the physical significance of the capacity, we did discuss about a binary symmetric channel, and there we provided some kind of an argument to show that error free transmission is possible, provided while transmission we do not exceed the capacity of a binary symmetric channel, correct? Okay. Fine. So, let us take a source which is a binary source, and it is a discrete memoryless source. So, the two symbols, let us consider them to be 0 and 1, and let us assume that the symbols are being emitted at the rate of Ts seconds, correct? Because a discrete memoryless source, the entropy of this would be equal to 1 bit per symbol, and the information rate would be equal to 1 by Ts bit per second, correct. Let us take this output of the source and feed it to the channel encoder, which has a rate R equal to k by n. So, we are going to take the input to this channel encoder in terms of blocks of k bits, and the output of that would be n bits, where n is larger than k. And let us assume that each symbol is basically transmitted every Tc seconds, correct. So, the transmission rate would be equal to 1 by Tc symbols per second. So, if we assume that we have a binary symmetric channel, then the transmission rate would be given by CTTC bits per second, where your channel capacity for a binary symmetric channel is equal to 1 minus Hp, where your P is the crossover probability or transition probability. Now, what does the channel coding theorem say is that the information rate, which is 1 by Ts, should be less than equal to channel capacity, which is equal to C by Tc. So, this implies that Tc by Ts should be less than equal to channel capacity C. Now, it is easy to see that your code rate, which is equal to k by n. So, k input symbols get mapped to n output symbols. The duration of each symbol here is Ts, the duration of each symbol here is Tc. So, this ratio is nothing but equal to Tc by Ts. So, what it implies from this, that your rate should be less than or equal to C, correct. So, your rate that is given by R, correct, it should be less than or equal to the channel capacity C, okay, fine. So, now let us take a illustrative example to highlight the significance of this channel coding theorem. Okay. So, let us say we have a binary symmetric channel with transition probability given as 10 raised to minus 2. Now, for this channel we can calculate the channel capacity as equal to 1 minus entropy function. This is equal to 1 minus h of 0.01, and this comes out to be 0.9192. So, in the light of the channel coding theorem, what it says that now you should be able to find a code with a code rate R which has to be less than or equal to 0.9192 to get almost error free transmission. That means make the probability of error as small as possible. Now, let us take a simple example of channel coding in the form of what is known as repetition code. Now, in this coding, what we do is basically any binary digit, say 0 or 1, is transmitted n times, correct. So, n is equal to 2m plus 1, where m can be 0, 1, 2 and all that. So, basically n is an odd integer. So, at the receiver basically we deploy what is known as majority logic decoding procedure, and the idea is that given n bits we decide in the favor of 0 if the majority of bits in this sequence of length n is 0, otherwise we decide in favor of 1. So, in such a case, for error to occur, it is required that m plus 1 or more bits out of n bits, which is equal to 2m plus 1, should go wrong, correct. So, because the channel is symmetric, so in this case irrespective of the a priori probabilities of binary digit 0 and 1, it is easy to see that the probability of error will be equal to summation of I is equal to m plus 1 up to n. This is NCI combinations. P is the transition probability of a binary symmetric channel, 1 minus P n minus I, correct. So, in the sequence of length n, this denotes I bits going wrong and this denotes number of bits received correctly. Okay. So, for this basically if we try to now for different value of m or indirectly n, if we try to find out the probability of error, we will get the result as follows. So, the choice of n will decide the code rate. So, when this is equal to 1, this is obvious 10 raised to minus 2, and when n is equal to 3, that means the code rate is 1/3, you can compute the probability of error turns out to be 3 multiplied by 10 raised to minus 5, code rate 1/5, this is 10 raised to minus 6, code rate 1/7, this turns out to be 4 multiplied by 10 raised to minus 7, 1/9 gives 10/8, 1 by 11 gives 5 multiplied by 10 raised to minus 10, correct. So, if we plot this probability of error versus the code rate, this is the curve which I will get. So, what this curve shows that as I keep on decreasing my code rate, the probability of error also decreases, correct. So, but if you look from the channel coding theorem, what we get is this red line. What it says that I have just taken a specific value of this this error to be 10 raised to minus 8. It is just without loss of generality, correct. So, this is the limiting value, correct. So, what it says basically that you can design a code or there exists a code for the code rate less than 0.9192, which is the capacity of the binary symmetric channel. You should be able to find the code such that the probability of error would be as small as possible, that is 10 raised to minus 8 in this case, correct. But what I get from the repetition code is this curve, correct. So, only it says this channel coding theorem helps me to know what is the maximum code rate which I can achieve, and that is equal to 0.9192 in this case. So far in our study, we have limited our discussion to discrete sources and discrete channel. In the next class, we will extend this to a continuous case. Thank you.